Hi all, and thanks for joining this webinar. My name is Christoph, and today Mathieu and I are going to talk about Speedgoat solutions for developing and testing electric motor controls. Electric motors impact almost every aspect of modern life. They power our vehicles, run our factories, and drive our appliances. Electric motors represent a large part of our electricity consumption. Electric motors and traction inverters are strongly impacting the overall efficiency of an electric powertrain. Here, engineers focus on achieving high efficiency, torque and power density while keeping overall system costs low. The traction motor and inverter are safety-critical components that require high coverage and repeatable testing to meet safety-relevant requirements. Ultimately, developing energy-efficient power electronics and smart controller software is a winning move in a competitive business environment. Real-time testing can accelerate your development cycles without compromising safety, costs, or quality. You want to test safely without risking damaging precious electrical equipment or prototypes? Test as early as possible to reduce the time needed for iteration loops and thereby your time to market. And improve your knowledge of the system to ensure its compliance with new requirements and regulations. Engineers increasingly rely on model-based engineering to address apparent challenges while keeping the pace of innovation high. They use digital twins to develop agile and safe electric motor control systems and test them. Yet, transitioning seamlessly from early requirements and integration testing remains challenging. What's needed is to stay within a single environment and automate testing end to end. The motor control development and testing solution by MathWorks and Speedgoat is designed to assist you with technical and workflow challenges. Benefit from a fully Simulink integrated solution that provides flexible and automated workflows. Powerful digital twin software and hardware emulation solutions, and modular hill racks that can scale with your needs. Let's look at a typical motor control development process. Speedgoats and the MathWorks motor control design and test solutions will you assist in this journey. We will use this visual throughout the entire webinar. Before your motor and drive are in operation, you typically start with modeling and simulation on the desktop, as shown on the left in this graph. A final step before commissioning your motor and drive is probably testing the system at full power with emulated motors, here shown on the right. We'll make sure to cover all intermediate steps for testing and designing throughout this webinar. Before we dive deeper into testing workflows, let's look into the agenda of today's webinar. First, I'll introduce the solution's key capabilities and workflows. We will then shift the focus toward testing electric motors and drives, and we'll cover these four areas: motor parameterization, rapid control prototyping, controller hardware-in-the-loop testing, and then power hardware-in-the-loop testing. For each topic, Mathieu will present a hands-on demonstration featuring Simulink and Speedgoat Test Systems. Okay, let's start with the capabilities. Suppose you want to test an embedded controller of a novel traction motor using the Simulink virtual vehicle. You do that by staying in Simulink without having to learn additional tools. You configure your model for real-time execution, select the appropriate hill simulator, and deploy your application to run on hardware directly from Simulink. Simulink blocks represent any I/O and protocols. Placing them in your model and configuring them is very simple. I/O support includes automotive protocols, fast analog and digital I/O, as well as emulating plant and fault insertion hardware. With over 200 I/O modules available, we ensure your workflows remain uninterrupted. Documentation and examples are accessible with a few clicks, integrated into the MATLAB documentation. Switching back and forth between desktop and real-time simulation is also very simple. For instance, we used system variants to switch between different testing scenarios quickly. Simulink isn't only your deployment environment, but also your hub for real-time testing using the same logging and instrumentation capabilities you were already using during desktop simulation. You can also open access to your real-time applications for non-Simulink users with tailored MATLAB apps. You can pack these as desktop apps or web apps that you share royalty-free with your test engineers. Simulink and MATLAB apps are great for interactive testing, but to reliably test your ECUs, you will need to automate testing. Considering these needs, the solution seamlessly integrates with MATLAB, Simulink Test, and third-party automation or continuous integration tools. Let's have a closer look. Because Simulink and MATLAB are so closely connected, you can quickly script actions, deploy and control hill tests from MATLAB. As demonstrated here, you can also interface your hill system with external programming environments like Python. So, suppose your team is using a different programming language. In that case, you can spend more time automating your testing and less time recoding in MATLAB. Scripting tests can be of great help, but for rigorous testing, you'll need a test automation suite that enables true end-to-end automation. Simulink Test is a great building block within the MathWorks ecosystem that can help you with this. It lets you create and manage test cases, perform requirements-based testing, and quickly create hill test campaigns for existing desktop simulation test artifacts. The assertion of results is fast and easy using inbuilt visualization tools, and you can automatically generate test reports and share them with stakeholders. You can also integrate with the third-party test automation tools using the ASM-XIL API. So this lets you flexibly build your hill system, reuse test campaigns, and available in-house know-how. Here I show the integration with ECU Test from Tracetronics, which some automotive customers have requested. You can further automate and boost the productivity of your testing using continuous integration. For instance, you can use source control within your projects, quickly track, compare and qualify changes, and integrate CI platforms like Jenkins, GitHub, or Azure DevOps to orchestrate testing and have hill systems operating around the clock. When developing highly integrated electric propulsion systems, compliance to industry standards is crucial. Our solution is being developed with these needs in mind. For instance, you find support for relevant automotive buses like CAN, CAN-FD, LIN, FlexRay, CENT, and Automotive Ethernet. Vehicle bus architectures are evolving rapidly too, integrating more AUTOSAR-based ECUs and complex multi-bus networks. When developing highly integrated powertrain systems, ISO 26262 compliance becomes crucial. The good news is that MATLAB Simulink, Stateflow, and the MathWorks verification tools are TÜV Süd certified, simplifying ISO 26262 compliance from ASIL A to D. Last but not least, MATLAB and Simulink support communication with ROS nodes via DDS middleware. In addition to MATLAB and Simulink, you benefit from an incomparable integration of additional MathWorks products that help you create and deploy high-fidelity digital twins. Toolboxes like Powertrain Blockset, Vehicle Dynamics Blockset, Simscape, and Motor Control Blockset give you quick access to customizable and hill-ready examples. These include component-level simulations of batteries, motors, and EV chargers, full electric vehicle models, as well as EVs integrated with the charging infrastructure and the power grid. You can also leverage available configuration tools to assemble custom full virtual vehicle models or battery packs, and integrate models with 3D simulation environments. The built-in library blocks let you simulate the components of various powertrain domains with different levels of fidelity. For instance, you can co-simulate thermal and electrical physical domains, simulate current ripples and high-frequency switching dynamics, and integrate high-fidelity models created with finite element analysis software. Additionally, these blocks support deployment to Speedgoat multi-core CPUs and FPGAs. Let us now closer look into the hardware capabilities of Speedgoat Test Systems. In general, Speedgoat target computers come with multi-core processors supporting concurrent execution and co-simulation with FPGAs. There's also extensive onboard connectivity, including several Ethernet-based protocols, serial and video interfaces. You can update and scale your system anytime with I/O expansion units or by implementing distributed simulation architectures. The PCI Express serial interface is the backbone for I/O connectivity, enabling the lowest latencies, fast analog sampling, and high-speed I/O. most scalable and performant system with highest I/O flexibility. It is the mainstay for hardware-in-the-loop testing, or hill testing in short. The mobile, baseline and unit machines are smaller and rugged, making them fit in applications requiring more portability and fewer I/O channels. The performance test system is suited for desktop use, but also for rack mounting. With the help of our project management and production teams, we can provide you with fully customized rack systems for hill testing, including easy access to all signals via breakout and I/O panels. We'll integrate power supplies, actuators, inverters, and any kind of power electronics, as well as project-specific PCBs for signal routing and conditioning. Let's move on to focus on the solutions for developing and testing electric motors and drives. In today's first demo, Mathieu will show us a typical modeling and simulation workflow. Specifically, he'll parameterize a motor model using some very neat Simulink features involving design optimization and automated parameter estimation. So, looking at the motor control development journey, we'll start with what's called desktop simulation. For our first demo, imagine you're starting designing motor controls using Simulink. To speed up testing and improve test results, you decide to create a high-fidelity model of your electric motor. Datasheet parameters gave you a good starting point, but you would like to refine model behavior with real motor data so the model becomes a true digital twin. So, Mathieu will introduce you to capabilities such as stimuli generation and on-target recording of real-time measurement data. He will then show how to use experimental data to automatically fine-tune parameters of your model. So, handing over to you, Mathieu.
Thanks, Christophe. Let's start by taking a look at the Simulink model used for desktop simulation. Here we have models for an early-stage field-oriented controller, as well as the permanent magnet synchronous motor, or PMSM for short. If we look inside the plant model, you can see that the motor is modeled as a Simscape network, which provides great model accuracy with the right parameterization. We have different ways to apply input signals to our model. For now, I want to manually define some custom control inputs. A quick solution is to use the signal editor block. As you can see, we have already predefined multiple signal scenarios, which we can select from the drop-down menu. Adding new signals and scenarios is also easy with the Signal Builder app. Here, I can, for example, add a blank signal and then simply drag and drop points and lines to build the signal. I can also draw freeform or use mathematical expressions. And you can always correct the values of each point manually in the table. For our test, let's just use the predefined coast-down scenario and run it. This will spin up the motor to a constant velocity and turn it off again. The deceleration curve depends on the motor inertia and the friction coefficients. If we compare the response of our Simulink model to the behavior of the real motor, we can identify these parameters to make our plant model accurately mimic the real motor. So to get the real motor response now, let's switch over to our other model variant. You can see it looks quite similar, but the plant model has been replaced with I/O interfaces to drive the real motor. I'm using a Speedgoat configurable I/O module, which is configured to enable PWM generation, quadrature decoding, and analog and digital signals. I'll set the stimuli to the same coast-down scenario and, with a single click, compile and run the model on the real-time target machine. You can see the video of the motor performing the experiment. We can use the Simulink Data Inspector to easily compare signals from different runs or to compare desktop simulation to the real-time application. The red line in the plot here is the rotor velocity from our real motor experiment, and the blue line is from our desktop simulation model. We can see that the generated signals speed up both the plant model and the real motor to a reference speed, but the coast-down behavior at the end is different, indicating that our parameterization of the motor model can still be improved. Now we could manually dig into the model, change some parameters and perform additional runs for comparison, but I want to introduce you to Simulink design optimization, which will allow us to automatically find an optimal set of inertia and friction parameters so that the response of the motor model matches the real device. Let's open the Parameter Estimator app directly from the Simulink toolstrip. To save us some time, I have prepared a session which is linked to the plant model, chosen the parameters we want to tune, and added the velocity data from the experiment with the motor. If we click Plot Model Response, we also get the simulation output from the current set of motor parameters. Now we are ready to start the optimization process. We can observe the progress in the plot. As the parameters are adjusted, the response of the digital twin gets closer and closer to that of the real motor. At the end, we have a new set of optimized parameters, which we can directly fill into the model, and our motor model will very accurately replicate the real motor's behavior. This model not only helps in early design stages of your controller, but can also be repurposed for later stages of development, such as hardware-in-the-loop simulation, which we will demonstrate later in this webinar. But now, let's get back to the presentation with Christophe.
Thanks, Mathieu. Note that the early modeling work is vital for later testing stages such as hardware-in-the-loop testing. For example, our customer Precise developed the world's first eye surgery robot using a very similar approach. While constructing a model of the robot's kinematic and dynamics, the engineers conducted system identification using Speedgoat target hardware with EtherCAD interfaces to excite the robot's motors and measure the response. The team then used the same target hardware to develop a controller model that processes inputs from a joystick and around 60 sensors and generates motor commands in response to the surgeon's movements. Our partners at Precise are not only happy with the efficient workflow that speeds up their development, but also about the solution robustness. Eye surgery is a field where trust in the solution and the patient's well-being are of utmost importance. Let's not waste any time and now focus on how to test control designs swiftly in the early stages. I'm showing again our overview visual. We are now transitioning to control design prototyping, which is often referred to as rapid control prototyping or RCP in short. At some point, you need to prove that your control design works well in real-world dynamics using the real motor and electric drives. When doing this, you will need to iterate on your designs, tweak parameters, and continuously monitor real-time performance. And this is exactly where you benefit from the close Simulink integration. It allows you to navigate seamlessly between control design testing and fine-tuning your algorithms. Let me hand over back to you, Mathieu, for a demonstration of rapid controller prototyping.
Thanks, Christophe. In this demonstration, I'll use again the model where we simulate our controller in real time and drive the real electric motor through the I/O interfaces. This time, we want to use the real-time workflow to perform rapid controller prototyping, meaning we want to change some control parameters and directly observe the changes in control performance. The field-oriented controller employs a PID control for the velocity control loop. At this point, we have already gotten a reasonable estimate for the controller gains through testing against our desktop simulation model. Now it is time to verify and fine-tune the control parameters against the real motor. What I want to point out here is that many parameters, such as the proportional and integral gains here, can be adjusted even during runtime of the real-time application, and changes don't require a rebuild of the model. I have started the model again. And you can see the motor and the live data from the simulation data inspector. I've added some dashboard controls as well to quickly change the speed command directly from the Simulink canvas, which allows me to see the effects of variations in the controller gains. Depending on your application, you might need to update multiple parameters simultaneously to test a desired effect. Apart from test automation, which we'll talk about later, this is also possible directly from Simulink. We activate batch mode on the real-time tab, and then we can adjust all the parameters we need. The changes will only be uploaded to the target machine once we click Update all parameters. To switch back to normal mode, simply click Batch Mode again to deactivate it. MATLAB and Simulink also offer you different tools for PID tuning and automatically find optimal control gains to achieve a desired response. And one more thing before we move on. I already showed you how we can modify parameters without rebuilding the model, but that's not all. Maybe you realized during simulation that you need to log some additional signals. This can be done at any time and without rebuilding the model. This is done by adding an instrument object and then simply selecting the signals by checking the checkbox. The selected signal will also be logged to the Simulation Data Inspector. You can also use the buttons from the Simulink tool strip to highlight existing instruments and add or remove them. Christophe, this wraps up the demonstration for this stage.
Thank you, Mathieu. You nicely covered some aspects that streamline testing. Updating model parameters during runtime or swiftly adding signals to be logged is greatly speeding up the workflow. So let's see now how developers leverage controller hill testing to validate the controllers. Now we are looking at our development overview again. At some point in your development, you will need to test the embedded controller. Also there, Simulink and Speedgoat can be of great help. On the screen, we see an example of a test system for controller hardware-in-the-loop testing, including the controller, an oscilloscope, and of course a Speedgoat hardware-in-the-loop test system. Mathieu is going to show the hill testing workflow for a PMSM drive. Mathieu, the stage is yours again.
Thanks, Christophe. The hardware setup for my next demo consists of a development computer running Simulink, Simulink Realtime, and an app to allow to instrument and monitor testing, a Speedgoat performance target machine with CAN and FPGA I/O modules, and a device under test, the TI Launchpad running the motor control algorithm. Last, an oscilloscope is connected to the analog outputs of the FPGA to monitor the motor currents. We set the speed command for the motor in the Simulink dashboard, and it is sent to the controller through the CAN bus. The motor controller will calculate the PWM to control the motor, and these signals are read through the digital input and control the gates of the inverter model deployed on the target machine. The motor electric currents are simulated in real time, converted to analog signals, and sent to the controller as feedback, as well as the quadrature digital signals. Let's now focus on the Speedgoat Test System setup. First, we will configure the interfaces for an ideal inverter. The ideal inverter will create currents from the duty cycle of the PWM. It does not model the individual gates, and the current will be the average of what the real currents would be. As the control algorithm has been designed with Simulink, you can easily simulate it with the inverter and PMSM models. To perform hardware-in-the-loop testing, we have deployed the controller to the TI Launchpad, so the algorithm will no longer be of use. But we need to set up the interfaces using the Speedgoat I/O block set. I am first going to use the setup block and select the appropriate I/O module. The configuration file defines its functionality as well as the pin mapping for the input and output connections to the real world. It can be changed to suit another test case or application at any time. The duty cycle will now come from the TI PWM outputs and will have to be captured through the digital inputs of the I/O module. We use the dedicated block for this. The currents need to be sent through the analog outputs. We first need the setup block and then link the currents in the model to the designated channels of the Speedgoat block. Last, we want the position feedback, and we will use the quadrature encoder block for this. We can now use this configuration to verify the deployment of the algorithm on the TI Launchpad and test the real controller performance. We have made a simple user interface directly in Simulink using dashboard components. It allows us to send the commands to the controller via the CAN bus. We can change the speed setpoint as well as the speed proportional and integral gains. On the right side, we display the information that the controller is sending back, such as the encoder counts as well as the calculated speed. This is very useful to debug any issues with the controller deployment, as we can compare it with the values from the model. We can even do some live tuning, and once we are satisfied with the controller, we can start automating the test. A convenient option is to use the Simulink Test Manager, which allows us to link the requirements to specific real-time tests and logical assessments. For example, a baseline test will compare the hill results with a simulated reference. Here, our requirements define a tolerance of 10% on the motor speed, which is represented by the green area of the result plot. As this condition is now satisfied, the requirement verification status turns to green. We are now satisfied with the basic performance of our controller. However, as we want to avoid any surprises in the final product, we will try to minimize current ripples linked to switching events, which can cause torque ripples in the motor responsible for noise and EMC problems due to unwanted harmonics. These types of investigations are very relevant for both robotic and vehicle applications. Observing current ripples requires a model of the inverter where each gate is dynamically switching during the simulation. To model these at high frequency, we need to deploy our plant model to the FPGA. For this task, we will use the template included in the motion control HDL I/O block set that consists of a model ready to convert to HDL. Let's get back to Simulink. The main component of the template is the green block, which contains the plant model that will be converted to HDL code that can be deployed to the Speedgoat FPGA. The blocks on the outside contain configuration parameters for the plant, like the motor characteristics, so that they can be modified even after the HDL code has been generated. We note here that the input and output ports have been named according to the physical interface that will be set later on. This template is ready to be deployed as is using the HDL Workflow Advisor. The first step corresponds to the target settings, where you get to choose the target FPGA and synthesis tool. In particular, the step 1.3 corresponds to interface parameters. This is where you need to map the input and output ports of the main block to the physical channels of your FPGA I/O module. In our example, we have prepared the template for the TI Launchpad. The next step sets the clock frequency of the FPGA, here 200 MHz, corresponding to the 5 nanosecond capture of the PWM. The last important configuration step is to add any additional source, like those of the Speedgoat code modules. Once the workflow finishes, you will obtain a generated model referencing your bitstream that you can add to your main model. The PWM is now captured with a resolution of 5 nanoseconds, and the motor and inverter dynamics are calculated with a 1 microsecond time step. We can therefore easily observe the large current ripples with high resolution using an oscilloscope or simulation data inspector using frame-based data logging. Observing and minimizing the effect of switching events can be particularly important in dealing with EMC or noise issues. Controller hill testing can also be used to observe the system's response to electrical faults in the inverter, which are complex and dangerous to test in an actual device. Our high-fidelity model allows us to shortcut the different legs of the inverter and verify if the controller will detect overcurrent situations. To further automate tests, you can integrate version control tools in Simulink to trigger your test and report creation from external platforms, and use continuous integration server to run MATLAB commands periodically or each time a change is made on the code repository. You can therefore trigger a test suite and check that the latest controller firmware validates all requirements. Christophe, this concludes my controller hardware-in-the-loop demo.
Thank you, Mathieu. Before deploying a new motor drive, it needs to be tested in a safe environment at actual power levels. This is where power hill testing comes into play. On the overview visual, we are now in the final stage of testing before deploying the solution. We'll be testing the drive at actual power levels, referred to as power hardware-in-the-loop testing, or P-hill testing in short. So, I'll be handing over to Mathieu again for an overview about Power Hill hardware and the final demo of today's webinar. Mathieu, you can take it from here.
Thanks, Christophe. Power hardware-in-the-loop testing is a vital step in the workflow because it is the last one before connecting the motor drive to the rest of the system. It is also the last option to test safety-critical aspects of the controller or simply to test a new inverter prototype in real conditions. Indeed, during Power Hill testing, using the amplifiers, the same currents will flow in the inverter as when it is connected to a real motor under load. Traditionally, you would require a motorized test bench to apply mechanical loads and to measure torque as well as speed. This type of equipment is expensive, and preparing a specific test can take hours or even days. In this demo, we show you how to test key functions of your motor drive, such as testing the overcurrent protection and setting up automated tests with predefined load profiles. For power hardware-in-the-loop testing with large currents and voltages, we integrate all components into a rack to benefit from additional safety. Here, the motor drive consists of a 3-phase 2-level inverter that is controlled by a compact Speedgoat target computer that runs the controller algorithm. The PMSM motor model runs on the performance real-time target machine, where its FPGA calculates the motor currents depending on the voltage coming from the inverter. The currents will then be generated by controlling the 3 power amplifiers which are directly connected to the output of the inverter. Last, we have installed current probes to measure the currents flowing from the power amplifiers on an oscilloscope. The electrical connections are wired in the back of the rack to allow a clean and safe integration and prevent accidental manipulation. The wiring represents the motor topology. We decided to test a delta configuration that creates higher inverter line currents at lower motor phase currents, therefore more demanding for the inverter. Inductances are added to allow the power amplifiers to correctly emulate the motor submitted to switching events. To recap, in our motor emulation demo, we test a motor drive consisting of a field-oriented motor controller and a 3-phase inverter using a power hardware-in-the-loop test system, where a motor model controls 3 current sources. We will test the motor drive against motor controller inputs, like the speed, setpoint, and PWM frequency, and we will also be able to change the plant operating conditions by applying a simulated load torque to the motor or introduce resistance fluctuations. Let us have a quick look at the models. To run the PMSM motor on the FPGA, we have prepared a source model where the inputs and outputs are configured. The phase voltages, which are acquired by dedicated sensors, are fed to the model through the analog input of the I/O module. The motor model will calculate the motor currents to emulate, and the position feedback will be sent using the quadrature encoder code modules to the digital outputs. They will be wired to the controller while the currents will be connected to the analog inputs of the 4-quadrant amplifiers. Last, we have also configured digital outputs to enable the power amplifiers directly from Simulink. The main model contains as well a user interface. It is used to control the power amplifiers and to modify the conditions of the simulation, like the external load and the motor internal electric resistance. The controller model is the standard field-oriented control using encoder and electric current feedbacks. we have added a management layer for the overcurrent faults that we want to use specifically in this demo. Before starting the power hardware in the loop simulation, we make sure that the safety is guaranteed. We first run the simulation on the plant's real-time target machine and turn on the amplifiers. From now on, the power hilt test system is emulating the motor. We enable the inverter, which will now react on the PWM inputs of the controller. We see that the motor starts to turn and follow the speed command. We reduce the PWM frequency to 1 kHz to observe the current ripples on the oscilloscope. Compared to standard controller hill testing, we are now reading real currents of a few amperes directly from real current sensors integrated in the power hill rack. Let us now experiment with the external conditions on the motor. Unlike with the physical test bench, we only need a few seconds to make drastic changes to both the controller and the motor in a completely safe environment. We first increase the load on the motor and see that the controller reacts by injecting higher currents. We reach our overcurrent limit of 9 amperes at roughly 20 cm². This is a good indication that our software protection works properly. We can now clear the faults and the controller gets the motor running again. Let's check the behavior of the controller and inverter when increasing the resistance of the motor. This could be due to an increase in ambient temperature or from a failure of the cooling system. The controller recovers without a fault. However, switching to open loop triggers a large current spike and a fault is detected. One last interesting test is to increase the resistance alone in open loop. As the resistance increases, less current can flow in the coils and the torque produced by the motor gradually decreases up to the point where the load will make the motor spin backwards out of control. These type of scenarios with the motor spinning out of control while connected to a real inverter are very valuable safety tests, but extremely hard to set up experimentally because of all the risk involved when mechanical parts take high rotating speeds. Motor emulation is a huge benefit for such cases. Now, to be more consistent, we want to automate such tests and run specific scenarios on demand. To do that, my preferred way is to use the signal editor to create scenarios and use Simulink tests to manage them, like we have seen in the previous demos. And here we set up a load profile like we would do with a controllable load on a real motor test bench. We then set up a Simulink test with a reference speed profile that will have to be matched with a certain tolerance. And simply run the test from a script or from the test manager. The test will activate the scenario and apply the load profile on the motor. We can see how the controller needs to cope with the load changes in real time, or simply look at the result once the test has ended. This type of test automation is very easy to set up using scripts or using the test manager. It will also create a report on demand. Here we see that the test has passed because the speed output matches the previously simulated profile within the tolerance. Let us recap what we have seen in this demo. We were able to verify the inverter design and performance by reproducing the behavior of a motor at the leads of our inverter and mimic full power operating conditions. We changed the switching frequency and observed the real current ripples and could confirm the synchronization and balancing of the three branches. We experimented with the load torque and resistance variations to verify the conditions for overcurrent fault detections. And last, we implemented a load profile to allow consistent test conditions and automated testing. Christophe, I'll now let you conclude this webinar.
Thank you, Mathieu. This was a very powerful demo that nicely outlined safe and efficient testing of the drive at actual power. I hope each of you obtained some tangible outcomes from the demonstrations. Let's now look into the key takeaways from today's session. There's a single key takeaway for you today. Speedgoat Test Systems and Simulink provide a testing solution for all aspects of designing and testing motor controls. Why is that? Well, you can model and simulate digital twins of your motors and drives, including ultra-fast switching dynamics in real time. You can develop and test in a single, fully integrated environment that fosters agile development and automated testing. Ultimately, Speedgoat Test Systems are performant, modular, and scalable. They allow you to prototype control designs, perform hardware-in-the-loop tests with your controller, and test your drives at full power. Thank you for staying with us until the end of this demo-packed webinar. You want to learn more about real-time controls testing? Then find additional content linked here.